So let's begin. Welcome again, everyone. Today is a very exciting lecture. It will be long and hard. Okay, so I would like you to pay attention and ask questions. I would like you to be interactive because we're gonna get in the middle of the curse of dimensionality. I don't know if you've ever heard of that word being thrown around. It's a very common word for those who are doing computing. Once you go from one dimension to two dimensions, it's like going from one kid to two kids. It doesn't get it's not twice the work. It's like 17 times the work. It's very incredibly more complicated, and it gets harder in three dimensions. So today I want to take the tools we developed to two dimensions. It's an experiment. I haven't done this before except for the like very senior graduate level courses like computational fluid dynamics. But with the tools we developed so far, we can totally do this. And I wanted to motivate you by showing you this calculation. So this calculation is hot off the press. I did that a couple of weeks ago, trying to prove that I can do full Navier-Stokes solutions with the tools that we developed. So this is flow over a circular cylinder. So cross section there. Imagine this is a rod or like a cable, a power cable, and there is air blowing from the left. So this would be similar to the bridge problem that we did. Hold on, let me animate this for you. More, repeat. So this would be similar to the bridge, the Tacoma Narrows Bridge. You see the vortex shedding being developed behind the cylinder. This is I didn't do anything here except put a cylinder and blow air from the left. So there's air coming from the left, and that oscillatory flow field automatically develops when certain conditions are met for the speed and the viscosity of the flow. But all of this was done with the tools that we developed. And I don't know if you were like me, I've always, like I growing up, I would see these calculations, these simulations and presentations that are like, I want to do this, I want to do this, I want to be the guy who's doing this. And hopefully you feel excited that you want to do something like this. Tell me, yes, I want to be able to do something like this. No? Okay, Abdallah, you can leave.
I'm
Okay.
actually doing something like this. So.
Okay. Well, we're gonna get into. It's one thing to use a commercial software to do this, which is okay. You know, most of you will be doing that. But I want to give you a flavor of what's going on behind the scenes. In that, it's not really that complicated. This is just a system of ODEs that we are solving at every grid point. Okay, so I want to take you in that direction today. We did the one-dimensional cases. We did advection, diffusion, and we did coupled equations with the diffusion reaction problem. So we've covered everything in 1D, and your homework assignment has a Dirichlet condition that's dependent on time. So you just have to figure out what you need to do at the boundary. So I think we're done with everything one dimension. Today we're gonna go to two dimensions. And in two dimensions, the same idea applies in that we will have a domain here represented in like this square domain, and I'm putting a grid point in the x direction, the y direction, but I need to crisscross those grid points. So because I don't have one dimension, for every x value, I have grid points in the y direction. So if you're going along the x-axis, for every grid point on the x-axis, you have a bunch of grid points on the y-axis. So you end up with something like this. An arbitrary point assignment is ij. We index I in the x direction, j in the y direction, k in the z direction. We're not going to go to 3D, so we'll stick with 2D. And the idea is the same. We are going to take a partial differential equation. I'm showing here an example of the diffusion equation for the species transport we did last time, but in two dimensions instead. Well, actually, this is not in two dimensions. Let me fix it. In two dimensions, I need to add the derivative in the y direction as well. Okay. All right. So this would be in 2D. This would be in 2D. I have I have diffusion in the x direction, that's the second derivative in x, and then diffusion in the y direction, second derivative in y. And together they're gonna diffuse whatever boundary and initial conditions I have. Now, before we get to the discretization, I want to get through some stuff programmatically from a Python perspective, because we really know how to do this. If you know the discretization in 1D, you just apply it in 2D. You treat the x direction as if it's one dimension. You treat the y direction. You do the discretization in y only, in x only, right? So it's because these derivatives. The derivative in x, you're holding y constant. The derivative in y, you're holding x constant. So you're really one-dimensional in each one of those derivatives. So we know how to do this. You just have to keep track of one more index, as we will see. But programmatically, from the Python perspective, there's some stuff we need to cover first. So in Python, 2D arrays that represent these grids are by default stored in reverse coordinate order. If you remember when we were plotting vector fields and scalar fields, I mentioned that to you. Maybe it didn't really stick, but we need to make it stick today. So in other words, point ij in this figure, do you want to access it in the array, you have to access it as j comma I, okay? Because they are stored in rows. Y goes in the rows, and then x goes in the columns, okay? And so you have to reverse the indexing. You don't store x first and then y. You store y first and then x later. That's what Python does it by default. You can change that, but I think it complicates things further down the road. So stick with this nomenclature and everything will just work as is. And if you remember mesh grid allowed us to create all of these grid points. So we say we want nx points on the x-axis, ny points on the y-axis. Create all of these, crisscross all of these points together. Remember, because at every x grid point, I need to have ny grid points. And so you're gonna crisscross all of those, and that's the most basic thing you need to do, because you need to have xy values at all of these grid points to build your initial condition, for example, because your initial Gaussian distribution is going to be a function of x and y, and they are in 2D, right? So you need all of those xy values. And the way we did this was with numpy.meshGrid. So let's say in x you do a linspace with nx points. You could do 10, 20, 30. And then in the y direction, ny points, however many, they don't have to be equal. And your domain size doesn't have to be equal here. They are of the same size. Lx and ly, they're the same size, but they don't have to be equal. Neither does nx or ny have to be equal. Okay. Now, so these x and y individually, they are one-dimensional arrays. To crisscross them to create this 2D grid, we do the mesh grid, and I store them in these. So mesh grid, what it does, it returns two arrays. Each one of them is two-dimensional, and I'm gonna call them here xx and yy. The first array, xx, contains the x coordinate for all of these points. So any point on this, any one of these blue points, the xx array contains the x coordinate for that point. And the yy array, at any one of these blue points, it contains the y coordinate for those points. Now together, you can pass them to an exponential distribution or a Gaussian, and you can combine them to create an initial condition. So let me give you an example, actually. So this is an example where my length on the x-axis is 1, and my length on the y-axis is 2. On the x-axis, I'm putting 3 grid points, and on the y-axis, I'm putting 1, 2, 3, 4, 5 grid points. Okay. Now, if I'm thinking about this correctly, the first x coordinate is 0, the second x coordinate is 0.5, and the third is 1. Now, this x coordinate is shared by all the points above it, right? Because if you go to this point at the next y value, it's going to be 0, 0, 0.5, and then 1, and then 0, 0.5, and 1, 0, 0.5, and 1, and so on. Now, along the y coordinate, my y ordinates values are going to be 0, 0.5, 1, 1.5, all the way to 2. But that also translates across all of the x points. Okay, so now let's look into what the xx and the yy arrays would contain. if you do the numpy.meshgrid and print the x-axis array, it's gonna look like this. It's a bunch, it's all the x coordinates, 0, 0.51, repeated 5 times. Why 5 times? Because I have 5 points in the y direction. So what this is doing, actually, this contains the x coordinates. The first entry in the x-axis array is all the x coordinates for the first y value, okay? The second entry in the x-axis array is all the x coordinates for the second y value, and so on. So that's how you see that Python is storing them y direction first and then in the x direction. Next, we go to the YY array. The YY array, I said, is going to contain the y values, okay, the y coordinate values at all of these grid points. So if you print it, this is what it's gonna look like. And now it looks a little different. However, look at that. The first row contains zeros, so that must be the y values, okay, for all the y coordinates for the first y value. Okay, so it corresponds to the y coordinate at these points, okay? And then all the y coordinates for the second y value, and so on and so forth. Does this make sense? So that's what XX and YY does. It stores in y first, and then it stores in x next. Okay. Now, I have a few, let me hide these slides. Let me put them a little later. I had a bunch of slides that I think I need to move for a little later. Okay. We will need a few additional things though. So after we do the numpy.meshgrid, now you've established your x and y coordinates. This is going to be incredibly important because your initial conditions are going to be dependent on those x and y mesh grid. We will create one or more ODEs per grid point. So if you had a system of partial differential equations in 2D, we will have to convert those to a bunch of ODEs at all grid points. And for each PDE, we're going to have nx times ny ODEs, right? And so the same thing when we did the coupled system in 1D, we can do it in 2D as well. For ease of interpretation, though, we are going to lay those ODEs on the grid as if we are dealing with IJ indexing. Now, this is the human perception of what the grid looks like. Solve IVP, unfortunately, cannot deal with two-dimensional arrays. Remember from the what we did last time when we did the coupled equations, we had to concatenate the ODEs into one giant list, a 1D array. Same thing for 2D. For 2D now we have nx times ny equations, and if we're building those equations on it using the 2D arrays, Solve IVP is not going to understand that. So we need to find a way to take that 2D array and convert it into a 1D array. Okay? So here's what we will do. We will do the discretization and do all the logical thinking on the 2D grid because that's easier. We're going to be using I and J, etc. We're going to operate as if we are working with a 2D array. Once we are done building the right-hand sides and the discretization and everything, with one line of code, we will convert this 2D, any 2D arrays we're dealing with, we'll convert them into a 1D array using something from NumPy called numpy.flatten. Okay, so we flatten the arrays that converts them into a 1D array. Okay, we will flatten the 2D arrays and send them to Solve IVP. Once Solve IVP is done, or as we are operating within Solve IVP is going to return a flattened array. What do we do to think about it and view it logically? We have to reshape it so it looks like a 2D array. So we need to go back and forth between reshaping 1D arrays and flattening 2D arrays. Okay, it's really not that hard as long as you remember that Solve IVP takes a flat array and returns a flat array. When we are working with discretization, boundary conditions, right-hand sides, we take that flat array, reshape it into a 2D array, work with it, then flatten it again and send it back to Solve IVP. So two additional tools we will need to use from NumPy. NumPy.flatten, it takes a 2D or a 3D array. So 2D array of size ny by nx, because our 2D arrays are going to be ny and x, right? And it will convert it into a 1D array of size ny times nx, okay? Because it needs to preserve the total number of entries. It just flattens it into a 1D array, okay? Now here the order doesn't matter because everything is going to be consistent, flattened consistently, so it doesn't matter. Now once we take a 1D array of size ny times nx, we can reshape it into a 2D array of size ny nx or nx ny. In our case, we're going to choose ny by nx, okay? We're going to take that flat array and reshape it into ny and nx because that's our storage convention. We store in y first and then in x, all right? So we're going to need these two, flatten and reshape, and once we do the coding, you'll get to see what we're doing, okay? Now, what about numpy.roll for the discretization? It still applies, thankfully. The same thing we did with 1D case. But when we had 1D, we had only one dimension to deal with. Here we have two dimensions. And if you remember, there was an additional argument in numpy.roll called axis. Axis is essentially in which dimension are you rolling, okay? If are you rolling in the along rows or along columns. Remember, our rows correspond to the y dimension and our columns correspond to the x dimension. So it depends now if we are approximating or discretizing in the x direction, we need to roll in the x direction. If we are discretizing in the y direction, so that would be y derivatives, we need to roll in the y direction, in the y dimension. Okay. Now, because of how things are stored in Python, Python stores rows first, so that's axis 0, and then columns, that's going to be axis 1. So our y dimension corresponds to axis 0, and our x dimension corresponds to axis 1. Okay? So discretizing in the x direction, remember always axis is 1, and discretizing in the y direction, remember always axis is 0. So let me give you an example. This is my XX array, okay, just that I gave you earlier, and I want to do an experiment. Say, what does it look if I roll it? Okay, so along the y direction, notice as y is changing, that axis is 0. Along the x direction, this is axis 1. So now if I roll along axis 1, what is it going to do? It's going to roll the last column. Notice the last column now became the first column, and the first column moved to the middle column moves to the last. See what happens? So 1, which was at the end over here, we rolled it by 1, so we moved everything to the right along axis equal 1. Okay. Now what would happen along axis equal 0? This is the YY array. Assume now we're discretizing in the y direction, so this would be advection in y or diffusion in y. Again, each term, you're going to treat it as if it's a one-dimensional discretization, but you just have one more dimension to just carry along, okay? So now if we were to roll this by +1 along axis equals 0, this is what will happen. It will move everything plus down by +1. Okay, so now 0, the first entry becomes the second entry and so on, and the last entry is rolled all the way through the back. Does this make sense? So we are rolling along the y-axis that corresponds to axis 0. Okay, it takes a minute to remember. If you forget, do a NumPy array example, 2D, and then test the rolling and see what it's doing for you. Okay. Now, I have a few other tips because we need to access boundary values. We need to access some boundary values. Sometimes we need to access all the values on the x minus or the left boundary. To do this, you do this slicing, phi semicolon comma 0. Why does this work? Remember, the first dimension in a 2D array corresponds to the y values, right? So here I want to access all the y values, so I put a semicolon on the y values, but the first x value, which is at index 0, right? So phi semicolon comma 0 gives you all the y values at x equals 0 at the left boundary. The opposite is true. On the right boundary, you're accessing the last x value, so you put a -1, but all the y values. So the way I read this, when I see this, I'm saying, okay, give me all the boundary points on the x plus boundary, on the right boundary. Okay, so for that, the x index is -1, but give me all the y values. Okay, you see the semicolon. Same thing in the y direction. If I want to access the bottom boundary, then what I will need to do is get the index of the 0y. So that becomes phi 0. Remember, because y is in the first entry in the first index. And then comma semicolon. So that gives me all the x values at the bottom boundary. And then the top boundary, you do phi -1. That gives me the last y entry, and semicolon on the x-axis. It gives you all the x values. Okay, that's it. That's all we need. Now, this is still a little bit fuzzy. It will be hardened once we do an example. So this is the example that we will do first. We're going to advect a blob, just like a blob, like a disk of values, all scalar, one, ink, drop of ink, and we're going to move it in 2 dimensions in a periodic domain. So like an infinite domain. Okay, so this is our working equation in conservation form, d phi dt plus div speed times phi. Now if the speed is a vector in this case, it's cxi plus cyj, so velocity in the x direction, velocity in the y direction. And if we assume cx and cy are constant, we can pull out c from the divergence, and then you get this simplified advection equation in 2 dimensions, d phi by dt plus cx d phi by dx plus cy d phi by dy. So cx d phi by dx is advecting phi in the x direction at the speed cx, constant, cy, so similar to the advection equation we did in 1D, now we're doing it in 2D. We're going to see what happens. Okay, on a periodic domain. I chose periodic so we don't have to worry about boundary conditions for advection. Like I said earlier, remember, advection we test with periodic conditions. Once we have diffusion, then we can put Dirichlet and Newman conditions. Okay, so how do I do this over here? Again, we're going to reason about the discretization on a logical grid that we can understand, and then convert that logic to Python indexing. All right? So I'm taking this and I'm going to discretize it at some arbitrary point ij. This equation is valid at any one of these grid points, okay? And this is the indexing. To the right of ij, I have I plus 1j. To the left of ij, I have I minus 1j. To the top of ij, I have I j plus 1. And to the bottom of ij, I have I j minus 1, okay? Logical indexing. Now, if I want to do upwinding on advection, which is what we've done, assuming velocities are positive, so moving from left to right, from bottom to top, then I'm going to do upwinding, which is a backward difference approximation. And then the advection term in the x direction, d phi by dx at ij, is simply a backward difference in the x direction. So j is fixed. I don't change j. The only thing that's changing is I. So the approximation is phi I minus 1 over delta x, while j is constant. So then in terms of 2-dimensional indexing, it's phi ij minus phi I minus 1j. You're holding j constant, but you're differentiating with respect to x. And we're approximating backward. So I minus 1. Same thing applies in the y advection term. Again, we're upwinding. We're assuming the velocity in the y direction is positive. So things are moving from bottom to top. And so we're going to do a backward difference in the y direction. So that's going to be phi j minus 1, the upwind value, the value below it, right? And I is constant. So it's going to be phi ij minus phi I j minus 1. It's exactly like one dimension, but you're only adding one additional index. That additional index is held constant because d phi by dy is the derivative of phi while x is constant. And this makes sense, right? It's d phi by dy. I'm only differentiating in the y direction. Okay? Is this okay? Does this make sense? We're just expanding to 2 dimensions. We have to tag along one additional index. Okay? So now we're going to be dealing with 2D arrays. Now, when you do the full discretization, it's going to look like this. d phi by dt at some point ij, and I should do this at ij, is going to be minus cx phi ij minus phi I minus 1j over delta x, that's advection in x, minus cy phi ij minus phi I j minus 1 over delta y. Now, this is going to guide us in how we're going to roll, because the first, the upwind in the x direction, we are going to be rolling in the x direction, which is what? Axis 1, okay? The upwind in the y direction, we're going to be rolling in the y direction, which is axis 0. And that's it. That's all you have to worry about, okay? All right, so let's do this. Let's actually just do this. Open up a Jupyter notebook, please. Open up a Jupyter notebook. Any questions? If you have any questions, just speak up, okay? Don't worry about interrupting me, okay? I want you to ask questions here. This is, I said, this is hard. If you don't exercise it, if you don't try it back, it's gonna take a couple of times. Once you do it 1-2 times, then it becomes easy, okay? And trust me, this is much easier than doing it the harder way, where you have to do integration. You implement your time integrator yourself. It's incredibly harder to do that. So I'm going to create a new notebook here, and I'm going to call it, what is it? Titled 1. Okay. All right, so I'm probably going to have to zoom in a little bit. I'm going to say this is example 5. 2025 in class, 2D advection. 2D advection will solve IVP. Okay, so we need to import our boilerplate. So you can grab it from another notebook if you want. And I added this animation piece. I don't know if you guys figured out the animation yet, but we'll talk about that once we get to the animation part. But this is my boilerplate, copy pasted from your any of your other Jupyter notebooks. And first, what I want to do, I want to declare some of my parameters. So I'm gonna put Lx equal Ly equal 1, and my advecting velocity in the x direction is 1, so that's meter per second. And my Cy, let's say it's 0, so I'm gonna test things out. I'm gonna turn advection on and off in each dimension to see if things are working, and then turn them on in both dimensions. And then Nx, let's say 64 grid points, Ny 64 grid points. And we said Lx equal Ly equal 1. And then let's do linspaces grid. So x is mp.linspace from 0 to Lx, and we're going to put Nx points here. And y is mp.linspace from 0 to Ly, and we're going to put Ny points here. Okay, and finally my so I need dx and dy. So dx is difference between any two entries in the x linspace, and dy difference between any two entries in the y linspace. Okay, and then I will create a mesh grid. I like to call them xx, yy. That's what I learned that actually from those who practice, who develop this mesh grid. It's to reinforce that this is your gridding, your crisscrossing x and y, x, y, y, kind of makes sense, and put them in capital. And that's mp.meshGrid. And with mesh grid, you just give it x and y, okay? And we can just execute this, and you can print xx and yy to verify what they look like. Next, I want to work on the initial condition. So we're going to build our stuff one step at a time. So I'm going to define a blob initial condition, and this blob is going to take a x and y. Now note, x and y are 2D mesh grid arrays. So I'm assuming x and y are two-dimensional. They're in the two-dimensional space. Okay, so how do I create a blob? How about if I take a disk? What's the equation of a disk? So I want to draw a circle in the middle of the domain, and I want to fill it with value equal 1, and outside it value equal 0. So what's the equation of a circle? You remember x squared plus y squared equal r squared for a circle? That's the equation of a circle. Now my circle is, that's a circle centered at 0. For a circle not centered at 0, the equation, so equation of a circle, it's x minus x0 squared plus y minus y0 squared equal r squared. Okay? That's the equation of a general circle. Now, everything inside that circle, so this is the equation of the circle. So at the circle, at the circumference, x minus x0 squared plus y minus y0 squared is exactly equal r squared. Outside the circle, that sum is greater than r squared. Inside the circle, it's less than r squared. So inside the circle, x minus x0 squared, does this make sense? Is less than r squared, right? So this implies that inside the circle, x squared minus r minus plus y, x minus x0 squared plus y minus y0 squared minus r squared is less than 0. Okay? So it's inside the circle that I'm going to put values of 1, and outside the circle, I'm going to put values of 0. Now I have the coordinates, x and y. So all I need to do is say where I want my center to be, okay? And then find out where that difference is less than 0, fill it with 1, otherwise fill it with 0. Okay, so let's do this. x0, let's put it in the middle of the domain, lx over 2, and y0 is ly over 2. Okay, and then let's say my radius is L over 8. Yeah, let's do L over 8. It's kind of reasonably small. If I do L over 4, then the diameter will be L over 2. Is pretty big circle. I want a small circle. So L over 8, let's say. And then finally, my disk is equal. So if I write this equation, my disk is equal x minus x0. Python is incredibly easy to use, that it's almost like magic. Like, huh? Like, look what I'm writing here. X minus x1 squared, okay, minus r squared. Okay, what is this going to do? This is going to create a two-dimensional array with values at each one of those grid points in blue. And those values are going to be either negative or positive. Okay, do you want me to prove that to you? I'm going to prove that to you. Okay, so I'm going to return this. Give me a second here. Okay, and so if I call blob initial condition with xx and yy, oh, L is not defined. R is Lx over 8, let's say. Okay, and then x1, oh, sorry, y0. Y minus y0. Okay, so now this is just simply a two-dimensional array with values. Okay, somewhere in these values, there's going to be negative values. There's going to be negative values. Now we don't see them here because it's a huge array. To see them, you got to put less grid points. Maybe we're still not seeing them. Put 16 grid points. Okay, so see, there's a negative value here. 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 Where those negative values are, we're going to put 1. And outside that, we're going to put 0. So I still need one more step here. I'm going to say my result is equal. So that's going to be my initial condition. If you remember when we did numpy.where or numpy.argwhere, so what numpy.where does, it returns elements where a certain condition is met. Okay, so what I'm going to do, if my disk is less than or equal to 0, where my disk is less than or equal to 0, return a value of 1, otherwise return a value of 0. Then return result. Okay, so let me show you how this is going to look like. So if I do a blob is equal blob initial condition with x, x, y, y, and then plt.imShow of blob, hold on, blob initial condition, blob. Look at that. The value, the yellow value is 1, the blue value is 0. Now, this looks ragged because it's a structured grid. Once you go to more resolution, 64, it's going to look more and more like a disk, like a blob. Okay? Magic. Python. And you're going to need this even if you're not doing scientific computing. Okay? Even with just like plain old data analysis, you're going to try to find where certain values are satisfied. Okay? If you haven't seen how to create a blob, now you've seen it. And now you remember it for next time. Okay, shall we proceed? Are you able to reproduce this? Okay, wonderful. Okay, so now we have our initial condition. We have our we have our initial condition. We have our mesh grid. It's time to build the right-hand side for the advection system. So define advection right-hand side 2D, and for this, by default, remember, solve IVP is going to pass t and phi, right? And then I need to pass along cx, cy, and dx and dy. Those are additional arguments that I need to pass on. Okay. Now remember, solve IVP works with 1D arrays. So phi that is coming here into this right-hand side is a one-dimensional version of the two-dimensional values of the grid. So now because my logic is going to work with a two-dimensional array, like I said earlier, we need to unflatten this array. We need to reshape it. So the first thing I will do is declare a new variable, call it phi grid, and simply say phi.reshape into ny and x. Okay. Now, let me give you an example, actually. Let's say A is a NumPy array, and it contains 1, 2, 3, and 4, 5, 6. Okay? So it's a 2 by 3 array, all right? And I can flatten it. I can say a.flatten. Okay. Oops. Sorry. Hold on. A.flatten is numpy.array. Oh, sorry. My bad. It's an array of arrays. Okay. Now, when I flatten it, it converted it into a, so B, let's say B is a.flatten and then print B. Okay, so that's B. That's the flattened A. Now I can B.reshape into 2 by 3. And then what it's going to do is going to give me back my original array. Okay? That's what we're doing here. Phi is the flattened version of my 2D array. The first thing I want to do is just convert it into a grid. So now I'm indexing in Ji. Okay? Now, advection. Let's do advection. Let's do du by dx. Now we said we're gonna do, this is phi I minus 1 over delta x, right? But I is axis 1, agreed? So be careful when we roll. So remember the 1D case, it's the same. So phi grid, this is phi I, right? Phi ij, essentially, minus numpy.roll, phi grid, and I'm going to shift by 1 because that's backward differencing, and my axis is 1. That's the only change you need to do from what we did in the 1D case. Remember, in 1D we did phi minus numpy.roll phi and shift 1. Here we called it phi grid because it's a 2D array, but it looks the same. There's nothing more mysterious than the 1D case except the axis. I'm rolling along the x-axis, okay? And then let's say d phi dx, and d phi dy now, again, is going to be phi ij minus phi ij minus 1. But j is axis 0. Agreed? So it's going to be phi grid, that's phi ij minus numpy dot roll, phi grid, and we're going to shift by 1, again, because this is backward differencing. Okay, shift equal 1, and then my axis is 0. So be careful you do that, otherwise you'll mess things up. And that's it. Right hand side is equal to minus cx times d phi dx minus cy times, almost unbelievable, d phi dy. Now return, I cannot, now our right hand side is a two-dimensional array. Now I need to flatten it to ship it back to solve IVP. Return RHS.flatten. That's it. That's it. It looks exactly, it looks 99% like the 1D version. If you disagree, you should say now and why. But I don't think you disagree, because it does look like the 1D version. Okay? All right? We are ready now to solve this. I'm going to delete these guys to clean up a little bit. All right, so now t0 is 0. And since my speed was 1 meter per second, okay, and my domain is 1 meter, my blob is sitting in the middle. If I want to have one residence time, essentially have the blob move by one domain length, my t final is 1 second, right? So it's moving at 1 meter per second. So it's gonna go and come back on the other side and get back exactly in the middle, okay? So let's do that. My t final is 1 second. All right. Now my initial condition is blob initial condition at x, x, y, y. Okay. Now then we do solve, and then t eval. Let's do evaluation at, 100 points, length space from from t0 to tf, and we do 100 points. And then my solution is solve IVP. And let's say, what does IVP want? Is the right-hand side, advection right-hand side 2D. And then my t-span is equal t0 to t final. And then my initial condition, y0, is going to be equal to u0. It's going to throw an error now, and I'm going to let it throw an error. My arguments are equal to cx, cy, dx, dy, because that's how I designed this right-hand side, okay? T and phi are default arguments. The remaining ones are going to be passed through here, all right? And then my t eval is equal t eval, okay? Now if I run this, it's gonna throw an error. It tells me y0 must be one-dimensional. I forgot to flatten it. Remember, u0 here is two-dimensional, so all I need to do is flatten it. Dot flatten. And if I run this, it runs. It runs. Okay, victory is ours. All right, so let's plot this. Let's plot this. Fig x or, hold on. So first, let's think about solution. So solution contains the solution in 1D in the first column and the times in the second column. So if I want to access, the solution, I need to also reshape to plot it in 2D because the solution is flat, right? So here's what I'm gonna do. I'm gonna create PLT, let's actually do it this way. Fig x is equal PLT dot subplots, okay, and then x dot contour f. And on the x-axis, I'm gonna put the x coordinates and then the y coordinates, x, x, y, y. Now I want to plot my solution. It's going to be sol.y. Again, the first column contains the solution. So I'm gonna get the entire solution at all the grid points. The second column contains the time index. So let's plot the initial condition. Now this gives me a flat array of size nx times ny. It's a flat array. I need to reshape it. So I can plot it on a two-dimensional grid. So I reshape as ny and x. Okay? And then we put, let's put 100 levels, and then put a jet map. And let's see what happens. Okay, look at that. That's my initial condition. Let's set the aspect ratio to equal. So this is a little trick. Okay, look at that. That's my initial condition. Agreed? That's what we wanted to start. That's what we started with. Is the initial condition. Looks correct. Let's take the first time step. Okay, oh, it moved, but the colors are all like messed up. I don't know why it's doing that. Let's go to 2. The color are still messed up. And then it's because of the 0, I think, but it's moving. It looks like it is moving. Okay. It looks like it is moving. Now, this always occurs, many of these cases. Let me see. So on my end here, okay, let me try this. Vmin is 0, Vmax is 1. Okay, it still didn't work. Still didn't work. -1. Okay. So, or 50, let's say at 50. Something is off. It's not moving. It doesn't look like it's moving. So this is at the end. Pardon me?
Sorry, is your dy all the way up? Is that supposed to be dy1 minus dy?
Yes. Thank you, Fiona. Thank you. Thank you so much. Good catch.
Yep.
Kudos to Fiona. Good job. Whew. Okay, so let's see now. It's still not advecting correctly. So let me check my code a little bit. So dphi by dx, shift 1, axis 0, phi grid, rhs dot. Yes?
Do the dphi dx and dphi dy need to
Yes, they need to be divided
the
by
dx and
delta
dy?
x. Yes, thank you.
Yeah.
Yes. Who was that? Eric? Yes.
Yeah, that was
Good
me.
job. I am doing this on purpose to get you guys to participate. Okay, now it's gonna work. Let me get rid of this stupid thing here. Position on screen. Okay, now it's gonna work. Ha! Yes, victory is ours. Okay, 0, and then after 1 time step, it starts moving, or like 3. Okay, can't tell, it's like moving to the right. Okay, it looks like it's starting to move to the right. It kind of messes up the things here. 50. Okay, it's moving now, and it's coming from the other side. But it's getting smushed. Why? Because of upwind. Remember, upwinding is gonna cause fake diffusion. It's going to smear it. But at least it's stable. Okay, it's going to smear it, but at least it's stable. So after 70 time steps, look at that. So it went to the right, and then it's coming back from the left boundary. It's coming in, and it's all smushed. Okay? It's all smushed in that direction. That's the price you pay with upwinding. Okay? That's the price you pay with upwinding. To correct for that, we need to do some advanced discretization, which is beyond what we need to do here. It's too much. And then the last time step, it came back to its beginning spot, but it's like looks completely different, okay? But at least what's true now is like, indeed, I'm advecting in the x direction. So now let's try to advect in the y direction. So this is sort of verification, making sure that we got this right. So I'm gonna turn on the y velocity and turn off the x velocity. Okay, I'm gonna run it again. Okay, look at that. So after 20 time steps, okay, it's going up. After 50, it's going up and coming from the bottom, right? Exactly as we expected, correct? And then at the end, the last time step, it got all the way over here, okay? Any questions? Okay, so now let's advect it in both directions. Let's put cx1 and cy1. It should go straight to the corner. Agreed? Symmetrically. All right? So let's do 1 and 1. Okay, and it's gonna diffuse a lot. All right, so let's do 0 here. And then it's gonna get really weird now because you are periodic in all directions. So you're gonna start seeing it show up from all sorts of weird ways. So after 10 steps, oh, look at that. It's going up towards the corner. 20 steps, still going up to the corner. 30 steps, okay. 40 steps. It's gonna start showing up from all of these weird other locations. Look at that. 50 steps. Eventually it's gonna come back through the corner. And then 70. Okay, it's coming back from the other side. Agreed. 80. It's come back, but it's completely diffused. Okay, it's completely diffused. And then finally it's back to where it started. So we are preserving the speed of the advection, but it's completely smooshed out. Okay, it's completely smooshed out. Okay. Now, in your homework, what you will do, you're going to solve similar equation, but I'm going to give you a very complex velocity field that's actually spinning, right? So you're going to see some really interesting effects going on. Okay. Was this hard? Was this cool? Good answer. That's the correct answer. Okay. Since you all answered the correctly, you're not going to get any extra points. Okay, so if there was one person who asked, so okay, this is so cool, right? Okay, so now let's go to advection, to diffusion. Diffusion is going to be more interesting because we're going to set non-trivial boundary conditions, okay? We're going to set non-trivial boundary conditions. So this is the 2D diffusion equation written with the correct sign. Like we caught the typo yesterday in the Stokes problem. So on the left-hand side, the diffusion is a negative, has a negative sign in front of it. On the right-hand side, has a positive sign. So this is the diffusion equation we will be solving. Now you should know that the Laplacian in 2D is the diffusion, and that translates to two second derivatives. Second derivative in x, second derivative in y. All right. So we'll follow the same procedure we did with advection. We're going to start with each diffusion direction at a time. Diffusion in x, that's second derivative in x. We know how to do this. You're holding y constant and you're doing that diffusion central approximation on x. So it's phi I minus 1 minus 2 phi I plus 1 at constant j. So you just carry that j along with you. Same thing as we did with diffusion in 1D, except now we're carrying a j. So when we are rolling here, we're just gonna roll along axis equal 1 because that's the ax diffusion, okay? And this is the stencil here in yellow, what points I'm using. I minus 1, I and I plus 1, all comma j, okay? Now, in the y direction, I'm using j minus 1, j and j plus 1, I is constant. Same thing over delta y squared, and we're not gonna forget to divide by delta y squared, delta x squared this time, okay? So that's it for x and y diffusion. So then this is going to be our ODE at every grid point, okay? Except the boundaries. The boundaries, we'll need to see what boundary conditions we have. So this is it. It's like doing 1D diffusion in x, 1D diffusion in y, except you're carrying a second index with you. Now we're gonna solve this on this domain, unit square, and these Dirichlet conditions. I just made them up. I put phi equal 1 on the left boundary, phi equal 0 on the right boundary, phi equal 2 at the bottom, and phi equal minus 1 at the top boundary, okay? What do we do at Dirichlet conditions? The right-hand sides are 0 at those boundaries. Now remember the slicing tip I gave you, how to access those boundary conditions. Okay, how to access those boundary conditions. We're going to use that to say the right-hand side at the left boundary is 0, but the initial condition at the left boundary is 1. Remember, with diffusion, when you have Dirichlet, the right-hand side is 0, but to achieve that boundary condition, you set the initial condition equal to the desired value. Right? So if d phi by dt equals 0 at the left boundary and the initial condition is 1 at the left boundary, the solution over time is always going to be 1. So that has the effect of implementing that boundary value at that boundary. And that's it. So we'll start with this problem. So let's go ahead and duplicate this file that we did, because we have all the boilerplate, the mesh grid, etc. And okay, where is it? 2D. Oh, Eric. Eric, you're back. Welcome back. You didn't miss much. All right, so I'm going to duplicate this file, and this is problem number 6. Okay, example number 6. I'm gonna put 6 here, example number 6. So if 2T diffusion with solve IVP. Excuse me. Okay, so this is still good. Over here, I don't have Cx and Cy. And by the way, you could have different diffusion coefficients in X and Y. Okay, you can totally have that. But in this case, we're gonna put just K. I don't know, let me see what I put here in my code. Let's say, 0.01. And you can have, like I said, diffusion in X, diffusion in Y, different coefficients. That's totally legit. So everything here is the same. I'm not gonna we can keep the blob initial condition if you want, that's okay. Now I want to do a diffusion right-hand side 2D. And for the diffusion right-hand side, what I need to pass is, so T, phi, and I'm passing K, all right, and then dx and dy as well, all right. The first thing we do is do this phi grid dot reshape, read, and then we add a comment, call it diffusion, okay. And now d2u by dx squared, if we go back to our 1D diffusion case, okay, so actually, let me do that to show you that it's identical. What is it? In class diffusion equation. So this is the example we did last week with 1D diffusion. I'm going to copy the answer from it. Okay. So blah, 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 here. This is what we did, right? So we had this guy, agreed, for the diffusion in 1D. So this is in class 2025, etc. So I'm going to take this and I'm going to put it here. I'm going to say this is K over delta X squared. So this is K d2u by dx squared is numpy.roll phi shift 1. So that's phi I minus 1. Now my axis for the x-axis is always 1. And then minus 2 phi. And this one, my x-axis, is equal to 1. Okay. Now I'm going to repeat d2 phi, call it phi, by dy squared is k over delta y squared. And I'm changing only my axis. Now my axis is 0 and my axis is 0 over here. Okay. That's it. Now we build the right-hand side is equal minus k d2 phi by dx squared minus k d2 phi by dy squared. Okay, we're not done because we need to set boundary conditions. Agreed? Okay, so for the boundary conditions, okay, everywhere on the left, right, bottom, and top boundaries, my right-hand side needs to be 0. Agreed? So Dirichlet conditions. Okay, so for the left boundary, I have right-hand side, all the y points on the left boundary, okay, all the y points at the left boundary, but the first x point. So that's RHS semicolon, comma 0 is 0.0. And then right boundary, that's going to be all the y values at the right boundary. So RHS semicolon, comma minus 1. So that's the last x value. Okay. Again, always remember we are indexing y first and then x. If anybody argues with you about this, tell them if you're using the default mesh grid, you are wrong. To change the indexing, you have to change how mesh grid is done, and I'll talk to you about that later, but most people are going to be wrong about this. Okay, this is the correct way of doing it. Their codes will not work once they change domain sizes and number of grid points in x and y direction. Their codes will crash. Okay. Now on the bottom boundary, I want all the x values at the bottom boundary. So all the x values at the first y index. So that's RHS 0, comma semicolon equals 0. So that's all the bottom boundary points. And then the top boundary, this will be RHS, the last y value, so -1, semicolon equals 0.0. Okay. Finally, return RHS.flatten. Give you a second to catch up.
Professor?
Yeah.
For the KD squared phi dy, would the shift be -1 for the first part?
No. So remember, there's the phi I plus 1 and phi I minus 1 are added. Phi I minus 1 corresponds to shift 1, and phi I plus 1 corresponds to shift minus 1. Now, it doesn't matter because they're symmetric. So if you put the first one shift minus 1 and the last one shift plus 1, it doesn't matter because it's phi I plus 1 minus 2 phi I plus phi I minus 1 or vice versa, right? So the phi I minus 1 and phi I plus 1, as long as you have shift 1 and shift minus 1, you're going to be good. Okay? So if you forget which one it is, it's good. But shift plus 1 is the phi I minus 1. I know it's kind of weird, but because you're moving everything to the right, so the last value becomes the first value. Okay, that's as if you're differentiating to the left. Okay, with periodic conditions. Yeah. Someone else said something? Anyone still working on this? Good? Perfect. Okay. All right, so I still have my blob, my initial blob, but I need to set my Dirichlet conditions now. Okay, my Dirichlet conditions. On the left, I had, what did I have? Phi equal 1 or something, right? What was it? Yes, so on the left, I had phi equal 1. On the right, I had phi equal 0, etc. So let's fix this. So on the left, it's going to be u0, all the y values, the first x value, and that's going to be 1. On the right boundary, I have all the y values and the last x value, that's 0. On the bottom boundary, I have the 0y index and all the x values, and that's equal to 2. And on the top boundary, I have the last y value, so -1 index on the first entry, and then semicolon for all the x values, and that's -1. Okay. And then we do this with the diffusion right-hand side, 2D, ... and then we have to fix this arguments here and put k. And you'll notice because diffusion is very slow on its own, we need to run this maybe for a longer t-final time. So I'm going to put it at 10 seconds for t-final. And if I run this, it's going to crash. I don't know why. Let's see why. Axis 1, outside boundary array dimension 1. Well, method vector. Okay, so it crashed over here. Oh, yes, I understand why. We had to use phi grid. My apologies. So phi grid, and then phi grid over here on the right-hand side. Make sense? Because we're dealing with the two-dimensional grid. Okay. Okay. Now it should work. Nope, it didn't work. Still another error. And this one, operands could not be. It's still giving me grief about this. Dot reshape and y and x.
It's still 2 times v instead of v good.
Pardon me?
Yeah.
In the routine, it's 2 times v instead of 2 times v good.
Yes, phi grid. That's right. Yep. Okay, perfect. Thank you, Ariana. All right. So now let's run it. Let's run at least the initial condition at 0. Okay, so this is my initial condition. Now notice it put some value at the boundaries, right? It put some values at the boundaries. Let's do a plt dot color bar. Let's see. Okay, so my contour is equal plt dot color bar my contour. Okay, so let's put 100 levels. Okay, so now this is gonna start diffusing. Let's do after the first time. Nope, it's crashed. Second time, it's crashing. And look at that, the values are insane because it became unstable. Why? We were using RK45. So let's change the method to BDF. Okay, let's change the method to BDF and see what it does. It's gonna take a little bit more time because this is a high resolution case. And 10 seconds is long. So you're gonna experience this in your homework assignment. Diffusion is generally very stiff. The larger the diffusion coefficient, the more stiffness you have. So, and the more grid points, the more expensive the calculation is going to be. So what we can do here, we can stop it for a second and reduce our resolution. Let's go 32. So we have less equations to solve and worry about. And I'm gonna do this for 1 second. Let me see. And then my K value was 0.01. Okay, let's see. Okay, so it ran. Okay, this is 5. It looks very, very weird because of this Vmin and Vmax. Okay, it's still giving me grief. Hold on, minus K H. So give me a second so I can figure this out. Oh, sorry, my bad. Plus. Never mind. Okay, I am sign challenged apparently. Okay, so initial you see the error? I had minus diffusion on the right hand side, which is always unstable. Okay, never mind. All good now. Okay, so now this is my initial condition after like 10 steps. So we're starting to see things are coming. There's some diffusion coming from the bottom and the left boundaries, right? Bottom and left boundaries. And then we go to 20 times, starting to diffuse. Let's go to the end. If you look at the end, you start seeing the diffusion from the bottom, the diffusion from the left. The blob is completely diffused now. If you run this for longer times, let's say 5 seconds. Let's run it again for 5 seconds. Look at that. It's going to diffuse, but then the top boundaries is negative value. So it's a sink, it's withdraw, it's cooling it off if you want. It's cooling it off. Eventually you're gonna strike a balance at steady state as if you have just a system of linear equations, but this is what it does. This is what's exciting about this, is that you can see the dynamics as time is changing through this. Okay, as time is changing. Let's put maybe 50 level. No, keep the levels 100. Yeah. Now, what I would do here is put the minima. Just keep it as is. Yep. And then you can run this. You can change your diffusion coefficient. If your diffusion coefficient is larger, it's going to diffuse faster. Okay, it's going to diffuse faster. If your diffusion coefficient is smaller, it's going to take more time to diffuse. The larger your diffusion coefficient, the more stiff your system of equations is going to be. Okay, so let me change so here we are at the end time, which is 5 seconds. So if I increase my diffusion coefficient, let's go from 0.01 to 1. So by 1 order of magnitude. Remember this state. with this new diffusion coefficient, it should have diffused even more. Okay, so let's see. Let's run it for the same end time. Okay, and if I run this, it's reached its steady state, but it diffused there faster. So it should have diffused there by probably half the time. In 2 seconds with the higher diffusion coefficient, it reached that state faster because diffusion coefficient is larger. So in your homework assignment, you're going to explore these options as you change the diffusion coefficient. How fast are you going to mix things up? If you bear with me for another 10 minutes, I need to cover Newman condition on this problem because it's a little complicated and you have to see how it's done for your homework assignment, okay? So if you bear with me a few minutes, please, we'll get through this. Okay, so now the next question is, I want now a Newman condition on the right, d phi by dx equal beta, okay? So this is identical to what we did in 1D, except we have to do it in 2 dimensions now. Okay, we have to do it in 2 dimensions. Okay, so the same thing we do, we introduce a set of ghost points on the boundary where you have a Newman condition, okay? And those red points, those are the ghost points, are obtained by getting the information from the Newman condition itself, which is d phi by dx at the last boundary, in this case at nx, for all the y values. That's equal phi ghost minus phi interior over 2 delta x. Okay, so you see this is phi nx plus 1, which doesn't exist. That's my phi ghost, minus first interior point on the right boundary. That's nx minus 1 j, all the j values, over 2 delta x equal beta. So call that phi ghost here, and then find the value for phi ghost like we did in the 1D case. Except now we're doing it for all the j, for all the y values, for all j. Okay? So what happens for your discretization on the right, you're still going to have to carry the diffusion in the y direction, but your diffusion in the x direction, you have that ghost point. Okay? You have that ghost point. Now, you might argue is diffusion along the boundary, does it matter? It doesn't really matter. So you can neglect that diffusion in the y boundary. So here I have a statement that you can neglect diffusion in the transverse direction at the boundary. So if you have a Newman on the bottom y boundary, you can neglect diffusion in along the x direction of that boundary and only diffuse in y. If you have a Newman on the x boundary, you can neglect diffusion in the y direction at that boundary only and only diffuse in x with the ghost point. Okay, so let's go ahead and try to implement this just at that plus boundary. Okay, just at that plus boundary. Okay, Newman on the right boundary. Okay, so now we can copy this from whatever we did in the 1D case. So my beta, let's say, is equal to 0 or 1. Okay, so then the slope, actually I want to put it equal to 0 because I want to show you something. Okay, let's put it at 0, and then my u ghost is going to be, if you remember the discretization here, my phi ghost was 2 beta delta x plus first interior point at all j values. So phi ghost, okay, is equal to what? 2 beta delta x 2 times beta times dx, okay, plus now I have phi grid. I want all the y points, so semicolon on the first index, but the second interior value, not the boundary value, sorry, the first interior value. So at nx minus 2. So this would be indexed at minus 2 in the x direction. Okay? So you're getting that interior value. So phi ghost minus phi interior over 2 delta x. Okay, so that gives you phi ghost. Then you fix the right-hand side at that boundary, same way we did with the one-dimensional case. So now my right-hand side at the right boundary across all the y values, so semicolon on the first index, but minus 1 on the second index. So that's the right boundary. Okay, so x minus equal -1 x index. Okay, and that's equal minus k over dx over dx. And I'm gonna apply this formula here, except I'm gonna be using only the boundary points. Okay, so what I would need to do is phi grid. I always said Newman conditions are complex. Okay, they take a little bit more work. Your homework assignment is only going to include Newman boundary conditions. Okay, so you have to repeat this process for the left, right, bottom, and top boundaries. Okay, but it's similar. The same logic applies. Except now we're not rolling. We're just gonna do it across all of those points at the boundary manually. Okay, so we will use slicing for this. So now I'm going to implement this equation here, the diffusion discretization. Phi nx minus 1 at all j minus 2 phi nx at all j plus phi ghost at all j. So that's going to be phi grid at all j values minus 2. So that's nx minus 1. Okay, minus 2 times phi grid again at all j, but at the boundary point, that's phi nx j plus phi ghost. Okay, phi ghost, I already computed that. Okay, plus phi ghost. I'm going to neglect diffusion in the y direction at that boundary. I don't care about it. Okay, there's no worries because it's the same Newman value everywhere, right? So there's no diffusion going on in the y direction. Okay, and that's it. That's all I have to do for Newman. So now my beta is 0 for the Newman condition, and I'm gonna run this for 5 seconds to reach steady state, and then I'm gonna plot the last value. Oops, I made a mistake here, sorry. It shouldn't be in minus, it should be a plus. My bad, my mistake, sorry. Again, I'm like sign challenged this year. Okay, so it ran. Okay, now what do you see? What did I tell you happens at Newman 0 conditions? What should the curve look like at a Newman 0 condition? If the boundary is like this and I have Newman, the curve should go up or go down. Newman 0. It should be perpendicular to it. Like Isaac was saying, you're doing this, right? Remember the 1D case. When Newman is 0, the slope is 0. So all my contour lines, look at them at the right boundary. They're going perpendicular to that boundary. Okay? Remember the 1D case. We did that on Tuesday. If Newman is 0, the curve was flat on the right boundary. If Newman was negative, it went down or went up, right? If Newman was positive, it went up, right? If Newman was negative, it went down. The same thing you see these contour lines, so let me put 10 contour lines. Look at that. Look at how they go in perpendicular to that right boundary. Okay? So now if my Newman is positive, let's put 1, then the slope is going to be positive over there at the right boundary. So let's test this. I ran it. Look at that. They're trying to go up, all of them. Agreed? That's going to be a telltale sign in your homework. Your contour lines need to obey this boundary condition. Now, if my beta is negative, they're going to go down. If I go -1, they're going to go down. Look at that. They are going down. Okay? As expected. Does this make sense now? It's a lot to take in. You have to repeat this, all of this by yourself. Put the video lecture, review it, the slides. Try to recreate that entire notebook. Okay? This is an experiment this year, but I think it's really powerful because all the interesting things happen in 2D and 3D. Okay, so having a tool that can allow you to understand what's going on in 2D and 3D is incredibly powerful. Okay? Okay, before I move on, I'm going to move on to one more thing. I'm going to talk about two things. So, now, what about the corner points? What if I had a Newman on the top boundary and a Newman on the right boundary. What do you do at the corner point? Don't sweat it. Whichever boundary condition is applied last is going to take over that corner point, and it's not going to matter. Okay, it doesn't matter. Don't worry about that. Those corner points are like singularities actually. Don't worry about them. Okay? Do not worry about them. Do not do any special treatment at the corner points. I have a statement about that in your homework assignment. Don't worry about the corner points. Whichever boundary condition you're going to apply last is going to take over whichever corner point is going to take care of. It's going to be fine. Okay? It will be fine. It's not going to affect your solution. Okay? So now, what next? Well, I'm going to show you the solution to your homework assignment. Okay? The solution that I worked up. And then I hope you can reproduce it in your homework assignment. So this homework assignment on Thursday is very heavy. Okay, that I'm gonna release today. It's going to be very heavy, and I'd like you to start on it immediately. It's gonna take a lot of work. So what you will be given is a situation like this: an isolated system. Okay, Newman condition equals 0. You're not exchanging energy and you're not exchanging mass with the surrounding. That's the power of that Newman condition. Okay? Now, if you have advection, it will pass through a Newman 0, but for diffusion, there's no exchange of matter at the Newman boundary, no exchange of energy, nothing going on. So it's like an isolated system. And I'm initializing my problem, half of it scalar value 0 and the other half 1. And I have a velocity field in the middle that's similar to you stirring your cup. Okay? So it's a velocity field that's going to spin. And I'm going to spin this initial condition. So assume you have T, perfect T on the one side, and you have a rectangular cup, some weird rectangular cup, okay, from Starbucks or us or something, okay? And half of the cup has tea in it, the other half has just water. And you release the membrane and you spin them, you're going to spin them at different speeds. Okay, or you're going to have different teas, types of tea that have different diffusivities, different diffusion coefficients. Okay? Now, I'm not going to give some of the answers away, but these things are going to mix and they're going to reach a certain average value. Okay? What you're looking here at the bottom are two cases. One on the left, it's the case where I'm stirring the cup very, very fast. And on the right, where I'm not stirring the cup at all. Okay? So the tea is just diffusing, taking its time to diffuse. So that's the bottom pictures. You can see the animation for that. On top, what you're looking at is a histogram of values, a density histogram of values in that domain. So initially, look at the histogram. Initially, I have all my values at 0, half of my values at 0, and the other half at 1. You see those two peaks in the histogram? There's one peak here, one peak there, one peak here, and one peak there. Look at the bin. At 0, I have half of the points. So half the grid points are at 0, and the other half, I'm just counting the grid points. How many grid points have value 0? How many grid points have value of 1? Okay? And as the simulation continues, things are going to mix and the values are going to change because they're diffusing and they're mixing. And I'm going to track how that histogram is changing, how many values on the domain are starting to change and to what value they're changing. Okay, so are you ready to run it? Okay, so I'm going to run it. So on the left, I have no advection. So that's no stirring the cup. Now notice my contour lines. They are perpendicular to the boundary because I have Newman 0. You need to check that. You have Newman 0. On the right, I am mixing, I'm stirring the cup. There's a velocity field that's spinning it. And it's spinning and diffusing. Now notice what happens. Look at the histogram. The one with advection, you're immediately getting to that average value. Everything is coming and peaking in the middle. And look at the time, within 0.78 seconds, 0.9 seconds, it reaches that value. The case with no advection, 1.4, it's still going, 1.7, 1.8, 2 seconds, and it still hasn't reached that final value. The lesson that you will deduce from your homework is how advection can enhance diffusion. What's happening on the right when you are mixing, advection doesn't mix. Advection just moves things from one part to another. But as it's moving things from one part of the domain to another, it's causing streaks. These streaks have more surface area to diffuse. So you have more opportunity for diffusion to do its job. That's why turbulence is very effective at mixing things. When you want to mix something, stir it violently. Why? With turbulence, you're creating a lot of these small streaks, and each streak has more surface area, giving more opportunity for diffusion to do its job. Okay? This is what you will demonstrate in your homework assignment. And you're going to find out that for a small k value and high advection, it's equivalent to having no advection but a very high k value. Because the only way, there's two ways to increase effective diffusion. It's either put a very high diffusion coefficient or a material that has high diffusion, and then or mix violently. Okay, I'm done. Thank you. Please redo this lecture. Promise me you will do that. Okay, please redo this lecture. Please redo this. This is very, very important. Okay, I'll release your homework, and I hope you're excited about this and scared a little bit. But instead of saying, oh my God, this is terrifying, you should say, oh my gosh, this is so cool. Make an animation, send it to your friends, tell them, look what I'm learning at the University of Utah. Okay, and I bet you no one else except maybe MIT and Stanford are learning like that. But like, okay, all the other universities, they're not learning this, okay? All right, thank you guys. Godspeed. See you on Tuesday. Have a good weekend.